Today we're going to be considering question 8 out of section 1.2, which reads as follows. Part 1. Show that the ring Z mod 4Z with 4 elements is not an integral domain. Part 2. Construct a field consisting of precisely 4 elements. The suggestion is to begin with the field F2 of 2 elements, and considering the set of pairs A1, A2 of elements A1, A2 in F2, with algebraic operations A1, A2 plus B1, B2 is equal to A1 plus B1, A2 plus B2. And A1, A2 times B1, B2 is equal to A1, B1 plus A2, B2 plus, and A2, B1 plus A1, B2 plus A2, B2. Remembering that minus A is equal to A in the field F2. An alternate way of describing the preceding algebraic operations is to write the pairs A1, A2 as A1 plus epsilon A2 for some entity epsilon, and to add and multiply these expressions as polynomials in epsilon, or it is assumed that epsilon squared plus epsilon plus 1 equals 0. This may remind you of the standard definition of complex numbers. So, take a couple seconds to try this out for yourself, then we'll do some hints, then we'll get on with the proof. Alrighty then, for some hints, we should recall what an integral domain is. That means it obeys the zero product property. And to construct the field, you should definitely go with the suggestion. I think that it feels easier to do the epsilon way of doing things, but you need to know some more things about fields in order for them to make sense. So instead, it might just be easier to work with pairs of objects for the whole proof. Alrighty then, let's begin. So to show that Z mod 4Z with 4 elements is not an integral domain, we simply need to find 2 elements whose product is 0, where neither of them are 0 themselves. And for this is easy because this is 0, 1, 2, 3. Here are 4 elements in Z mod 4Z. We note that 2 times 2 is equal to 0, but neither 2 nor 2 is 0. Therefore, it is not an integral domain. Next, let's do a little construction using the second half of this proof, even though it won't continue that way. It's nice to know why an alternate way of describing this. So you consider polynomials in epsilon. When you're considering polynomials, you need to indicate what field you're doing this over, and we're going to be doing it over the field F2. So that means that this expression can be written as epsilon squared is equal to epsilon plus 1, because we're in F2, so minus A is equal to A for all elements. Therefore, when you subtract the epsilon and the 1 from both sides, you actually put them on the right side as positives. So that's how you can kind of generate the idea of this product rule, in the sense that if you simply FOIL out A1, A2, let's write this in the way they want it, which is A1 plus epsilon A2, A1 plus epsilon A2, and you multiply that by P1 plus epsilon B2, you see you'll get terms A1 B1 plus epsilon squared A2 B2 plus epsilon A2 B1 plus epsilon A1 B2. And so in the way you recover this is you use this identity. We've just shown that epsilon squared is equal to epsilon plus 1, and then distribute that here. So you get A1 B1 plus A2 B2 plus epsilon outside of A2 B1 plus A1 B2 plus A2 B2. And then you see that this is exactly the same construction, where the first element is going to be A1 B1 plus A2 B2, which is the non-epsilon elements, i.e. those without an epsilon on them, and then everything with an epsilon can be written like this. So you see that these are equivalent ways of writing them. But let's actually proceed. To prove this of fields, we need to show associativity, commutativity under addition, identity elements, inverses, and distributivity. So associativity, we're going to skip, because associativity simply comes down to the fact that we know that all these elements are taken from a field. So for instance, A1 plus B1 A1 plus B1 plus C1 can be written as A1 plus B1 plus C1, or A1 plus B1 plus C1. And in doing so, we're just applying the associativity of F2, so that's pretty trivial. And then we're going to say the commutativity of addition also follows, in the sense that commutativity addition, we're simply going to apply the commutativity of the addition in the field, in the sense that A1 plus B1 is equal to B1 plus A1 in F2. Therefore, we're not really going to concern ourselves with it, since it's again pretty trivial. It's just applying properties we already know the elements obey. Note that our definition of field for gunning does not have commutativity multiplication in it. Next, we should show the identities. So the identities are elements such that if you add them to any element or you multiply by any element, you get the same element back. So for the additive identity, we're going to be checking this out. And we see it's pretty clear that B1, B2 should equal 0, 0. So we say our additive identity is 0, 0. And we can check that works on both sides, and we'll be all set. Next, for the multiplicative identity, this feels a little more complicated since the second term is so crazy. But we'll note that when we multiply by our identity element, B1, B2, that we want to be left with A1, A2. And if we look at the second term, we see that A2 is attached to B1, and the rest of the terms are attached to a B2. And in this one, A1 is attached to a B1, and the rest of the terms are attached to a B2. So therefore, we can let B2 be 0 and B1 be 1. And we see that when we multiply, we get back the exact same number. We get back the correct number. So we have a right inverse for A1, A2. And that will work. And then we can check if we want to see if it works as a left inverse. Well, we see that the first term, if it was 1, 0, where A1 is 1 and A2 is 0, we get back a B1. And the right term, we see that the A1 term is left with the B2, so we're left with the correct thing. So this is a left and right inverse for multiplication. I'm sorry, left and right identity for multiplication, which it should be, because identities we should have multiply on the left and the right. Next, we'll do inverses. So inverses, for addition, we note that A1 plus B1, we want that to equal 0, 0, but we'll recall that minus A is equal to A, so we simply let for any element, A1, A2, its inverse is also A1, A2. Because when you add that to itself, you always get back 0, 0. So that's pretty fast. Finally, we're going to check the multiplicative inverses. Note that we need multiplicative inverses for all non-zero elements. And instead of just trying to prove this for a general case, it's usually a little bit easier to just write these all out. Since there are only 3 of them, it's not a terrible exercise to try to do it yourself, though. It's just a little more complicated. You need more logical operators to do it. So let's take 0, 1. I want to see what we have to multiply it by to get 1, 0. Well, we want the first element to be 1. We need A1, B1. Whatever A1 multiplies is going to be 0, so it doesn't matter what we have there, whatever B1 is. So we look at A2, B2, and so we want to have a 1. Therefore, we should have this be we should have B2 be a 1. Next, we see that B2 is 1, so we get A1 plus A2 is going to be 1 plus 1, and that's just going to be 1. So you have a 1 term there, and we want the second term to be 0, so A2B1 should also be a 1, because 1 plus 1 is 0 in F2. Therefore, A2 times B1 is going to be, we want it to be 1, so we have 1 times 0, 1, your options are 0, 1, so it should be 1, and you get your answer. 0, 1 times 1, 1 is going to give you 1, 0, which is our multiplicative identity. And then you can actually check really quickly that this also works in the other direction, that the inverse of this is this. And finally, we'll check the last possible option, which is what is the inverse of the identity element. But of course, we know that the identity element squared should be the identity element, so we get this relation. And we have all of our inverses for multiplication, and then these are given by these sets. Finally, for distributivity, it's a little less trivial, it's a little more calculation, but is not particularly enlightening to see, so I'll leave that for you to prove for yourself. With that, thank you for watching.